now the bomb has exploded. Instead of answers, astronomers and cosmologists are constantly being served up new puzzles and shocks these days. Now, the concept of an isotropic universe is also on the brink of collapse, and with it, one of the fundamental pillars of our cosmology.
अच्छा.
Isotropy assumes that the universe looks the same in all directions, regardless of where you look at it from. This assumption is a fundamental part of the cosmological principle, which states that the universe is homogeneous and isotropic if we look at it on a large enough scale. For example, the cosmic microwave background radiation pattern looks uniform everywhere, and large clusters of galaxies are also distributed almost uniformly across space. At least that's how it used to look, and scientists then turned these observations into basic mathematical rules to simplify scientific descriptions of the universe. But this may have been a stupid mistake. The observations of Adam Rees and other scientists researching accelerated expansion have initially confirmed the isotropic model, at least in part because the measurements of supernovae have shown consistent results with regard to the rate of expansion. This means that there appears to be some kind of isotropy. However, the expansion is much faster than it should be according to old physical assumptions. The end of dark energy? It remains exciting in science. In order to understand the puzzle of the new cosmology, we need to take a closer look at dark energy. The exact nature of this energy is still unknown, but its existence and properties are crucial if we want to understand how and why the universe expands in an isotropic way, and why researchers came up with the current standard model of cosmology. Dark energy is a hypothetical form of energy that could be present anywhere in the universe and very likely plays a key role in current theories about the expansion of the universe. It's thought to be the driving force behind the accelerated expansion of the universe. By acting against gravity, it pushes the cosmos apart. In current cosmological theory, dark energy is responsible for about 68% of the total energy content of the universe. Here you can already see a problem. Scientists blame almost 70% of the energy processes in the universe on an energy whose existence has never been proven. An important element supporting the existence and properties of dark energy up to now was the observation of Type 1a supernovae as carried out by Adam Rees and colleagues. The accelerated expansion observed here could not be explained without the effect of a large repulsive force. Further evidence that this mysterious energy really exists was provided by the cosmic microwave background radiation and other large-scale structural studies. However, recent observations by the James Webb Space Telescope have now shaken the concept of dark energy. The JWST can observe the early universe in a level of detail that was previously unattainable. Even the first precise observations revealed structures and objects that are older and more developed than they should be according to the standard model of cosmology. These observations could indicate that the universe may have expanded even faster or originated at an earlier time than previously assumed. All these results indicate that we have not yet understood some crucial elements and forces in the cosmos, including dark matter and dark energy. It's very likely that we are now facing a complete revision of the standard cosmological model, but we are not ready for that at the moment. We can't come up with new theories because we don't have enough tangible information about what's new. Will we find the answer in the world of quarks? So the revolution in our worldview will have to wait a little longer. Only when Webb provides us with more images and researchers make even more incredible discoveries will we be able to piece together a new picture. That may take time. In the meantime, researchers around the world are searching for answers that are already available. David Gross is another scientist who welcomes the crisis and sees it as an opportunity. Gross points out that the answers to the great mysteries of the universe are not hidden in the macrocosm, but in the microcosm. The renowned theoretical physicist is an expert in the theory of strong interaction and string theory. He is also one of the Nobel Prize winners and received the award in 2004 for the discovery of asymptotic freedom in the theory of strong interaction. The discovery was fundamental to understanding the behavior of quarks, which are the basic building blocks of protons and neutrons. These particles are the main actors in the standard model of particle physics, and they are the basis of everything we can see and measure in space. Consequently, the basic structures and principles of the macrocosm must also have counterparts in the subatomic realms. The concepts that Gross helped to develop deal, among other things, with the events shortly after the Big Bang. Realize that there were no stars and no objects in the universe at that time. For hundreds of thousands of years, there was only an extremely hot primordial soup in which particles flitted freely through space without forming bonds. Before the Big Bang, there was presumably only a kind of quantum fluctuation in which all forms canceled each other out in such a way that, from a physical point of view, they amounted to zero. With the Big Bang, this quantum fluctuation fell apart, and particles packed with charges and forces shot into an otherwise empty space. These particles later became stars, galaxies, planets, and life forms like us humans. Is Gross right when he says that these particles are the answers to all the questions? Probably yes. But how do we study the behavior of particles that were in space 13.8 billion years ago? Among other things, researchers use the cosmic microwave background radiation. This is considered to be a fairly accurate reflection of the events shortly after the Big Bang, and has probably not changed much since then. However, quantum physicists and classical physicists do not quite agree on how to interpret this imprint of the early days of the universe. At the moment, the situation in science is that quantum and particle physics cannot be reconciled with traditional cosmology. The findings from the world of formed matter do not fit with quantum physics, or rather, the binding link is missing. David Gross is convinced that this bridge can be found in previously unknown particles and forces. He was one of the researchers who worked hard to reach a consensus between the disciplines even before the debate triggered by James Webb. As co-author of string theory and in a coherent unification of quantum mechanics and general relativity, he was keen to close the gap between the two worlds and disciplines of science. Gross's work on asymptotic freedom describes how quarks behave at very high energies. This is fundamental to understanding the early universe shortly after the Big Bang, when energies were extremely high. His theories can clarify as yet unclear aspects of the expansion of the universe. However, there is some controversy among scientists, as the theses of string theory are too far-fetched for many classical physicists. David Gross suspects that the answers to all unanswered questions lie in the quantum fluctuations within the microwave background. The CMB fills the entire universe and can be found in all directions around us. The cosmic background explorer